Hi students, welcome back to geology. We are working on our last plate boundary here in this video. We're looking at convergent plate boundaries, what happens when plates collide. So your pondering question here I want you to think about is how did the Himalaya mountain range get so tall? So as we go through this and we talk about the different interactions at convergent plate boundaries, I want you to think about that. Again, we're working with the lithosphere, which is the crust and uppermost mantle that makes up our tectonic plates, and it moves along the asthenosphere, which is our ductile, mechanically weak upper mantle. Okay, the cookie is the lithosphere, the cream filling is the asthenosphere. And we've already talked about divergent plate boundaries and transform plate boundaries. Now we're going to focus on convergent plate boundaries, which destroy, we call them destructive margins. They destroy crust, and this is due to compressional stress, so pushing together. Divergent was tensional, construction, creating crust. Conservative margins at transform plate boundaries, where things are just sliding past each other in shear stress. Now we're destroying rocks. So at convergent plate boundaries, we have three different interactions that we focus on. This is where two tectonic plates are colliding or coming together. Okay, so this is important to remember. Where two plates are meeting, we're going to see a lot of different things depending on the interaction. Is it continental-continental, oceanic-oceanic, or continental-oceanic? Okay, so neither plate is going to create, let me not say that. Not neither plate, but when the two plates interact, depending on what they're constructed of, whether they are basalt, which is oceanic crust, or they're granite, which is continental crust, you're going to see different things being created. So let's kind of go through that kind of slowly. So let's revisit divergent plate boundaries are at the mid-ocean ridge. They are pulling apart. You can see convective cells working in the mantle here. And then we're over here on the left where plates start to come together and things are diving back down into the center of the earth. Okay, so we're going to start with our continental-continental collision. So here is where two continental plates are colliding. So think of taking the cookie, breaking it in half, and trying to push it together. Okay, so you're pushing that cookie together with doing nothing else to it. Right, so you have two continental crusts pushing together. And what's going to happen is first you're going to have upward push. So you're going to have mountain ranges start to create. In a mountain building event, we call that an orogeny. And during that process, mountains start to uplift or lift up into the sky. So that's what uplift means. And one continental crust will be slightly more dense. And when that happens, that one will slide underneath just so. So you can see there on the left, one of the continental crusts is sliding underneath the other. And this isn't going to be a very steep angle because most of the push is up. Okay, we're not going to see volcanism happening here, but we're going to see really large mountain ranges being created. So around 70 million years ago, India, which is a large land mass, took off north and made a beeline for the Eurasian plate. And starting around 20 million years ago to present, we saw the push up or uplift of the Himalaya mountain range. And that continues today. So India continues to push against the Eurasian plate and push these mountains up. One of the really good pieces of evidence that we have that this is how the Himalayas originated was that at the peak of the Himalayas is a bunch of oceanic fossils. So fossils, marine fossils that were found at the tips, which indicates that India must have plowed through the ocean, pushed all of that material up to the tips of the Himalayas. So uplift continues today, although the rate of erosion, so how quickly things are being weathered at the top, is happening faster than the uplift right now. So that's how the Himalayas came to be. When we look at oceanic collision, so this is two oceanic plates collide, a lot of different things start happening. So oceanic plates are made up of basalt, they're heavier, and so we have two things pushing together that are dense. And so one of them is going to eventually sink down. And when that happens, we have earthquakes, of course. We have a trench being formed where the two plates are meeting. Okay. And the other thing that's happening is that water is entering the mantle. And the water is coming from hydrolyzed minerals that used to be on the ocean, bottom of the ocean floor. Okay, so on top of that oceanic crust, the rocks have experienced more water than rocks that are on the continent. When that happens, that water enters the mantle as that material goes down, and then it lowers the melting temperature. And we call this flux melting. When that happens, mantle material rises as magma, and it creates volcanoes. So with oceanic collision, we have hydrolyzed minerals going down at the mantle, lowering the melting temperature, allowing for magma to rise, and it creates a volcanic island arc. On either side of that arc, we have a forearc basin, which is on the side of the trench, between the trench and the island arc. We have the back arc basin, which is behind everything, on the other side of the volcanic island arc. And then the last piece that we have here is what we call an accretionary wedge. So an accretionary wedge is all of the material on top of the oceanic plate that is subducting gets kind of stuck in that trench and scraped off. So if you imagine a conveyor belt that you put a bunch of sand on top of, and you allowed the conveyor belt, like at the grocery store, to come back around, all that sand's going to get stuck where the conveyor belt tries to return. And that is what creates the accretionary wedge. It's all that sand that would get stuck in the conveyor belt that is the trench. All right, so an example of this on Earth is the Mariana Trench, which is the deepest trench on Earth. To give you some perspective, it is taller than Mount Everest, or deeper than Mount Everest. The elevation of Mount Everest is about 8,900 meters, and the Mariana Trench goes down more than 10,000 meters from the ocean surface. It's a very deep trench where two plates are colliding, and these are oceanic plate collisions. Another example in the United States is the Aleutian Islands, which is the tail of Alaska. And so here we have the Pacific plate subducting beneath the northern part of the North American plate. And it creates the chain of islands, and those are the volcanic island arc. And then lastly, we have convergent plate boundaries where oceanic and continental plates are meeting. Where oceanic and continental plates meet, there is a big discrepancy between their density, and so the oceanic plate dives into the mantle at a very steep angle. Okay, so a lot of the same things are created at oceanic continental collisions that are created at oceanic collision, but it's a little bit more exaggerated. So the interaction here, we call this subduction. So it's creating earthquakes. It's bringing hydrolyzed minerals into the mantle still. It's got volcanoes being erupted on the continent, so we call them continental volcanic volcanoes. And we also have an accretionary wedge, which is that little green piece there where the trench is. We have a forearc basin and a back arc basin. All of those things are still the same. But the intensity of the earthquakes that are produced here are much higher because the oceanic crust is diving more steeply into the mantle, which is creating deeper seated earthquakes because rocks are rigid at a deeper point in the earth. And the deeper the earthquake originates, the greater the ground shaking will be, or the magnitude will be. So we call this zone of earthquakes the Benioff zone. And it is a swarm of earthquakes that are on top of that oceanic plate that's subducting. So you can see all those dots that go down. That's the Pacific plate subducting beneath the Australian plate, for example, near Australia. And you can see the red earthquakes that happen close to the surface are going to be lower in magnitude. The blue ones that are further into the earth, deeper in the earth, are going to produce a higher magnitude. So where is this happening? This is still happening in North America. So this is, I know I've shown lots of other places on Earth, but this is happening in North America. The Juan de Fuca plate, which is a subdivided plate in Northern California, Oregon, Washington, is subducting beneath North America, and it's creating the Cascades. So the Cascades in California include Mount Lasta and Mount Shasta. Some examples in Washington are Mount St. Helens and Mount Hood. And then there's plenty more cascade volcanoes, but these are some of the more popular ones that people know. All right, so it's important to understand the Earth is dynamic. So understanding that even though I say this plate is interacting like this right here at this point in time, it wasn't always that way. So because Earth is dynamic and things are moving, sometimes plates are pulling apart, they run into something else and move a different direction. And when we look at interplate volcanism next, that'll kind of hopefully make a little bit more sense. So in summary, remember divergent plate boundaries pull away from each other, they create new crust. Convergent plate boundaries push against each other and they destroy things and create a lot of volcanism. Transform plate boundaries slide past each other and they don't create or destroy anything outside of earthquakes. So your final thoughts in your notes: compare oceanic continental and continental convergence in one sentence. Okay, so think about that, and I will see you guys in the next video. Bye.